Hello, my name is Gyanaranjan Priyam, and today I will be walking you through my machine learning project proposal. A smartphone based crop disease detection system designed to help small scale farmers identify plant diseases early and take corrective action before significant crop damage occurs. Crop diseases are basically one of the leading causes of agriculture losses and responsible for destroying up to 40% of global food production annually. Small scale farmers in rural and developing regions are especially vulnerable because they lack access to expert agronomists who can diagnose plant disease in the field. By the time a disease is visually obvious and identified, it has often already spread, significantly leading to devastating yield losses and financial hardship for farming families. The problem I am addressing is a very specifically defined. Given a smartphone photograph of a crop leaf taken by a farmer in the field, can a machine learning model accurately identify whether the plant is diseased and if so, what disease it is, so that the farmer can take immediate targeted action? I consider this an attractive opportunity for machine learning for three reasons. First, there is a clear and measurable problem with significant consequences. Crop disease cause real quantifiable financial loss, and early detection has a direct and proven impact on reducing that loss. Second, this is an pattern recognition problem at its core. Distinguishing between healthy and diseased leaves based on visual features like color, texture, and spot patterns. This is exactly the kind of task where deep learning models, specifically called convolutional neural networks, that is CNN, trained on image data, have demonstrated exceptional performance. In fact, publicly available datasets like the Plant Village dataset, which contains over 50,000 level images of healthy and diseased crop leaves across 38 classes, make this a tractable problem to approach immediately. Third, the solution is practically deployable. Virtually every farmer today, even in rural areas, has access to a basic smartphone. A lightweight ML model embedded in a mobile app requires no expensive equipment and fits naturally into farmers' existing workflow. Moving into the crisp DM business understanding phase. The core problem is the small scale farmers cannot reliably identify crop diseases early enough to prevent significant yield loss due to a lack of access to agriculture expertise. The key stakeholders are the farmers themselves, agriculture extension services, and NGOs or government agencies that support rural food security. The constraints include the need for the model to work reliably in low bandwidth or offline environments, the need to handle images taken under variable lighting and field condition, and the need to support multiple crop types and disease relevant to the target geography. The business question we are answering is, can we build a model that correctly identifies the disease present in a crop leaf image with sufficient accuracy to be trusted and accepted upon by a farmer with no agronomical training? For output matrices, the direct measure of model performance, I would track classification accuracy, but more importantly, recall per disease class, since missing a serious disease like late blight in potatoes is far more costly than false alarm. I would also track top 3 accuracy, since suppressing the correct diagnosis among the top 3 suggestions is still highly useful for a farmer consulting the app. For outcome metrics, the real world impact, I would measure the reduction in crop yield loss among farmers using the app compared to a controlled group not using it, as well as time from first visible disease symptom to correct treatment action. These outcome matrices capture whether the model is actually helping farmers protect their crops, not just whether it performs well on benchmark dataset. There are several factors potentially relevant to model performance. These include the crop species and variety, the geographic region and the climate, the growth stage of the plant, the time of the photograph, the quality, the resolution of the smartphone camera, lighting condition in the field, and the presence of multiple diseases simultaneously on the same leaf. These factors must all be considered when collecting training data and engineering features to ensure the model generalize well across the diversity of real world conditions it will encounter. My solution concept is a mobile application powered by a convolutional neural network, that is CNN, specifically a fine-tuned mobile net or efficient net architecture chosen for the lightweight footprint suitable for mobile deployment. It accepts a photograph of a crop leaf and returns a disease classification along with a recommended treatment action. To validate this concept, it, iteratively, I would execute the following experiments. In the first experiment, I would train a baseline model on the publicly available plant village dataset and measures its classification accuracy on held out test set. This establishes a performance benchmark. In the second experiment, I would conduct field testing with a small pilot group of 20 to 30 farmers in a targeted region, providing them with the app and asking them to photograph disease plant in real condition. I would compare the model's diagnosis against ground truth labels provided by an expert agronomist, measuring how well lab performance transfers to a real field condition. In the third experiment, I would gather qualitative feedback from the pilot farmers on usability, trust, and whether the recommendations were actionable. This validates not just technical performance but a real world utility. Each experiment informs the next iteration, adjusting the training data, the confidence threshold, and the user interface based on findings. For my three key ML system design decisions. First, cloud versus edge. I would deploy this as a primary edge-based system with the model running directly on the farmer's smartphone. This is critical because rural farmers often have limited or no internet connectivity in the field. An edge deployment ensures the app works offline and delivers instant predictions without network dependency. A lightweight architecture like mobile net makes this feasible even on low-end Android devices. Second, offline versus online learning. I would usually offline batch training where the model is periodically retrained in the cloud on newly collected and labeled field images, and then the updated model is pushed to device when connectivity is available. Full online learning on devices is not appropriate here because individual farmer would not generate enough data to meaningfully update a model, and quality controlling field collected labels in real time would be extremely difficult. Third, batch versus online prediction. Prediction must be generated online in real time the moment the farmer takes a photograph. A farmer standing in a field cannot wait for a batch processing job to run overnight. The entire value of the system is instantaneous in the moment diagnosis, which requires real time interface at the edge. I anticipate several potential risks once the model is in production. The first is data drift. The visual appearance of a crop disease can vary significantly by geography, soil type, climate, and crop variety. A model trained primarily on images from one region may encounter disease presentation in another region that look different enough to cause degraded performance. Continuous collection of new labeled field images from diverse regions and periodic retraining will be necessary to address this. The second is concept drift. New crop diseases or new strains of existing diseases can emerge over time. For example, a new fungal strain with slightly different visual characteristics, the model would have no exposure to these new disease presentation and would misclassify them, potentially recommending entirely wrong treatments. The third is training servicing skew. The training data, even from the plant village dataset, consists of high quality, well lit, cleanly photographed leaf images taken under controlled condition. Real farmers take photos outdoors with shaking hands, poor lighting, partial occlusion, and dirty lenses. This mismatch between training condition and serving condition could significantly degrade real world accuracy and must be addressed by augmenting training data with realistic field condition images. Monitoring these risks through ongoing collection of field feedback, model on confidence, score tracking, and periodic expert validate audits of model outputs will be essential to maintaining the trust and performance over time. In summary, a smartphone based crop disease detection system is a narrowly defined, partially deployable, and high impact opportunity for machine learning. It addresses a real problem with measurable consequences, leverage the proven strength of deep learning in image classification, and is deployable through a channel, the smartphone, that is already in farmer's hand. By designing it as an edge system with periodic offline retaining and real-time on-device interface, and by and by proactively planning for data drift, concept drift, and training serving skew, we can build system that is not just technically sound but genuinely useful in the field. Thank you.